the most important but the most incompletely understood concept in all of science. Having discussed in part 1 thermal entropy arising from the energy level distribution of particles in a sample of matter, in this part 2 we will consider positional or configurational entropy, which arises from the spatial distribution of those particles in the given container of a particular volume. We will perform a Bottzmann analysis and employ the Bottzmann entropy equation to thoroughly and clearly understand positional entropy. Recall from part 1 that the equation is S equals KLN W, where W is the number of possible microstates, namely the number of ways in which the particles of the system can exist in the given macrostate. Each microstate of the particles conforms with the macrostate that the system is in. To make the analysis simple enough, let us say that the initial macrostate of a system is a gas consisting of just 4 particles, which may be atoms or molecules in the left compartment of a container, while the right compartment is empty. The 2 compartments are separated by 2 closely spaced partitions, the left one having a hole that can allow 1 particle to pass through at a time, but blocked by the partition on the right, which can be removed when desired. The volume of the left compartment is V1. The volume of the whole container, namely the total volume of the left and right compartments together, is V2. The temperature of the container is kept constant so that, as discussed in detail in part 1 of this video series, there is no change in the energy level distribution of the particles of the gas, and therefore S thermal remains constant and delta S thermal equals 0. As discussed in part 1a, to carry out the Bottzmann analysis of this system, let us label the 4 particles as A, B, C, and D. In terms of a crude analysis, there is only one way in which this distribution can occur, with A, B, C, and D all being in the left compartment. We will later consider a finer, more precise analysis. Since the particles are indistinguishable, it does not matter which of the 4 particles on the left is where exactly in space in that compartment. All possibilities such as ABCD, CBAD, DBCA, etc. correspond to the same description of the macro state, namely that A, B, C, and D are all in the left compartment and hence collapse into just one possibility. In the finer analysis later, we will assign specific positions in space to each particle and consider the total number of possible microstates, which will be greater than 1. Thus, in this case of crude analysis, the number of possible microstates W equals just 1 and SV1 equals KLN1 equal to 0. Now, let us say we remove the partition on the right so that the hole on the left partition is no longer blocked and one particle at a time can pass through to the right compartment from the left. This results in various possible distributions corresponding to the larger final volume V2. It can be seen that there are totally 4 possible distributions which we will refer to as D1 through D4. In D1, there are 3 particles on the left and 1 particle on the right due to the passage of just 1 particle. In D2, there are 2 particles on each side constituting a uniform distribution. In D3, there is 1 particle on the left and 3 particles on the right. Finally, in D4, all the 4 particles are on the right with the left compartment being empty. Now, let us analyze the number of possible microstates corresponding to each of the above 4 possible distributions. In the case of D1, it does not matter again in this crude analysis which of the 3 particles is exactly where in the left compartment. All possibilities correspond to the same one microstate that says they are all in the left compartment. While doing the Bottzmann analysis, it is important to keep in mind that it is always easier to consider the smaller number of particles to work out the number of possible microstates. So, in this case, consider the 1 particle on the right rather than the 3 particles on the left for the analysis. Since the 1 particle on the right can be either A, B, C, or D, the number of possible microstates W1 equals 4. In the case of D2, corresponding to 2 particles on either side, the possibilities for, say, the left compartment are AB, AC, AD, BC, BD, and CD. The combination, for example, BA, will duplicate the combination AB, since in either case the description is the same, namely A and B are in the left compartment. Therefore, it should be avoided. The same way, CA duplicates AC and so on. The duplicates can never be included in the count, of course. Also, notice that it is always better to consider the possible combinations in a systematic way in order to avoid both duplication and omission. Start with A for the first one and consider B, C, and D respectively in that order to combine with A. Then consider B for the first one and combine C and D respectively in that order, omitting A, which has already been considered. Then consider C for the first one with which D is combined, omitting both A and B since they have been already considered. Automatically, the remaining two particles in each case should be placed in the right compartment. Therefore, the number of possible microstates for D2, namely W2 equals 3 plus 2 plus 1 equal to 6. For D3, with 3 particles on the right and 1 on the left, W3 is the same as W1, since it does not matter if that one particle is on the left or on the right when it comes to the number of possible microstates. Thus, W3 also equals 4. For the last possible distribution, D4, with all 4 on the right, W4 is equal to 1, which is the same as for the initial state. Therefore, S1 equal to S3 equals K ln 4 equal to 1.386 K. S2 equals K ln 6 equal to 1.792 K. S4 equals K ln 1 equal to 0. In the final volume V2, W V2 equals 15. As discussed in part 1b, at any given instant, the particles of the gas will be in one of the microstates of D1 or D2 or D3 or in the microstate of D4. The OR operator implies addition of the microstates of the various possible distributions, not their multiplication, which is associated with the AND operator considered in detail in part 1b while illustrating the second law using 2 lead or 2 silver blocks. And SV2 equals K ln 15 equal to 2.708 K. Thus, when V1 increases to V2 during expansion, SV1 equal to 0 increases to SV2 equal to 2.708 K. Whenever volume increases, entropy is always observed to increase also. Boltzmann analysis and his entropy equation help us understand this thoroughly. The three simple interpretations of entropy discussed in part 1 of this video series can explain the increase in positional entropy with an increase in volume. In a larger volume, the particles obviously have a greater degree of freedom of motion. And from the energy dispersal point of view, one can look upon this as a greater dispersal of the energy possessed by the particles throughout a larger volume instead of being concentrated in a smaller volume. And the random motion of the particles might be considered to be more disorderly in a larger volume. Using the Clausius definition of entropy change, one can derive the equation for the change in entropy accompanying a change in volume from Vi to Vf during an isothermal process undergone by an ideal gas. Accordingly, delta S sub T equals Nr times ln of Vf over Vi, similar to the equation for delta S sub V or P considered in part 1. An algebraic analysis of this equation shows that, as in the case of delta S sub V or P, when Vf is larger than Vi, as for expansion, their ratio is greater than 1 and its logarithm is positive. Since N and R are always positive, delta S is positive. This implies that S increases during expansion, as we saw above with the help of Boltzmann analysis. For compression, Vf is smaller than Vi and their ratio is less than 1. The corresponding logarithm is negative, implying that S decreases. Recall from part 1b that according to a postulate of statistical thermodynamic theory, each of the above 15 microstates is associated with equal probability of occurring. Therefore, the probabilities for the 4 different distributions in V2 are 4 over 15, 6 over 15, 4 over 15, and 1 over 15 respectively. D2, which corresponds to a uniform distribution of particles, is the most probable distribution and associated with the highest possible entropy. Since the W's and hence the P's are not too different in this case, all 4 distributions occur. As the number of particles increases, the number of possible microstates also increases. For example, when n equals 6, the number of possible distributions in V2 equals 6 corresponding to 5, 1 with 5 particles in the left compartment and 1 in the right, then 4, 2, 3, 3, 2, 4, 1, 5, and finally 0, 6. The number of possible microstates respectively are 6, 5 plus 4 plus 3 plus 2 plus 1 equal to 15, then 40, then 15 again, 6 again, and finally 1. W total therefore equals 83 and S equals KLN 83 equal to 4.419 K, which is higher than 2.708 K for 4 particles. Again, D3, which is the uniform distribution with 3 particles in each compartment, is the most probable distribution with a probability of 40 over 83, and it has the highest entropy equal to 3.689 K among the 6 possible distributions. And when the number of particles is very large, namely of the order of Avogadro's number, there is one particular distribution for which the number of possible microstates is humongously huge compared to that for any other possible distribution, and the system exhibits this most probable distribution all the time. This happens to be the uniform distribution of the particles. This is like the Bottzmann distribution in the case of thermal entropy discussed in part 1. This uniform distribution in space at the microscopic level determines all the macroscopic properties of the system at the macroscopic level. Since, according to the second law of thermo, every spontaneous process in nature tends to reach a state of maximum entropy, the equilibrium state corresponds to this uniform distribution associated with maximum entropy. Our observation has always been that whenever a gas expands, the final equilibrium state is characterized by a uniform concentration and a uniform pressure throughout the container. Also, when we prepare a colored solution such as blue copper 2 sulfate solution or yellow potassium chromate solution, the color is uniform throughout the solution at the equilibrium state. Both of these are simply due to the uniform spatial distribution of the gaseous particles or the solute particles. Thus, Bottzmann analysis and his entropy equation elegantly explain these facts of nature. It is not easy to understand this in terms of disorder or freedom of particles or energy dispersal. In fact, some may even look at the uniform distribution like a more orderly arrangement of particles. In order to improve the above crude analysis of positional entropy into a finer, more precise one, it is customary to imagine the container to be made of tiny cells, each of which can snugly hold just one particle. Let us say that the initial state corresponds to Vi of a tiny container consisting of just 6 cells and n equals just 2 particles in that volume Vi to make the analysis simple enough. In how many ways can the 2 particles be spatially arranged in Vi? That is, how many microstates are there corresponding to this macrostate of n equal to 2 and Vi equal to 6 cells. Since the cell number serves as the label for the particle occupying it, we do not need to label the particles as A and B. Just the circle representation of the particle itself will suffice. Both particles are indistinguishable from each other. Therefore, when we consider any given pair of cells, for example, the first and the second, it does not matter if particle 1 or 2 is in the first cell with the other in the second. The microstate is one and the same since the description in either case is the same, namely that the 2 particles are in the first 2 cells. When one particle is in the very first of the 6 cells, the second one can be in the second, third, fourth, fifth, or sixth cell, resulting in 5 different microstates. When one particle is in the second of the 6 cells, the second one can be in the third, fourth, fifth, or sixth cell, leading to 4 different microstates. In this case, we should not consider the second one in the first of the 6 cells, since it has already been taken into account when we consider the first particle being in the first cell in M1. Keeping this important rule in mind to avoid possible duplication and continuing this analysis, it is seen that next we get 3 microstates, then 2, and finally just 1. Therefore, Wi equals 5 plus 4 plus 3 plus 2 plus 1 equal to 15. Applying Bottzmann entropy equation, the initial entropy Si equals K ln 15 equal to 2.708 K. Now, let us say that the volume increases to Vf containing 8 cells. A similar analysis shows that WF equals 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 equal to 28, and SF equals KLN 28 equal to 3.332K. Thus, an increase in volume always leads to an increase in entropy due to an automatic increase in the number of microstates. Notice that W in each case happens to be the sum of the first n natural numbers such as 1, 2, 3, etc. This sum is known to be n times n plus 1 over 2, which of course always increases as n increases. Thus, this finer and more precise analysis also, like the earlier crude one, shows that an increase in volume always leads to an increase in W and hence S. When both the temperature and volume of an ideal gas change, the resulting change in entropy is the sum of the corresponding changes in thermal and positional entropies. The change from the initial state I to the final state F can take place through any path. Two such paths are shown as path 1 and path 2. Although it is very difficult to calculate the delta S for such a complicated path, we can imagine the change as taking place in one of two specific unique ways. In path 3, T is first changed from Ti to Tf at constant Vi, for which we can calculate delta SV using the equation in part 1b, and then V is changed from Vi to Vf at constant Tf, for which delta St can be calculated using the equation mentioned above. On the other hand, in path 4, V is first changed from Vi to Vf at constant Ti, for which delta St can be calculated, and then T is changed from Ti to Tf at constant Vf, for which we can calculate delta Sv. Delta S, which is the sum of the two, can be calculated using either path 3 or path 4. It will give the same value, and it is the same value for paths 1 and 2 as well as for any other path, since S is a state function, as long as I and F are the same. Whenever any number of substances mix together at constant temperature, the positional entropy always increases. This can be easily understood using Bottzmann analysis and his entropy equation. To illustrate this, let us consider the mixing of two gases at constant temperature in an isolated container with two compartments. Assume that the molecules of the gas in the left compartment are red colored and those of the one in the right compartment are green. Let us also assume that both kinds of molecules are of similar size. The two compartments contain 4 cells each. To make the analysis simple enough, let us assume that there is just one molecule of each gas. W R for the red molecule equals 4, since that one molecule can occupy any of the 4 cells. Similarly, Wg for the green molecule also equals 4, since that one molecule can occupy any of the 4 cells. Si equals Sr plus Sg equal to KLN4 plus KLN4, which is 2.772 K. Or alternatively, Wi equals Wr times Wg equal to 16. Therefore, Si equals KLN16 equal to 2.772 K. Now, the two gases mix together when the partition is removed and the two molecules occupy a total of 8 cells. If we consider red to be the first molecule, then the number of possible microstates with green being the second equals 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 equal to 7 times 8 over 2 equal to 28. Next, the first molecule can be green and the number of possible microstates with red being the second is also the same 28 as before. In this case, since the positions are fixed and the molecules are distinguishable, red-green sequence is not the same as green-red sequence. These possible arrangements have to be counted separately. Therefore, Wf equals 28 plus 28 equal to 56 and Sf equals KLN 56 equal to 4.025 K. Thus, the positional entropy increases from the initial 2.772 K to the final 4.025 K due to mixing in this isolated system. Notice that since the entropy increases during this process, it can take place spontaneously in any isolated system itself, similar to the heat flow from hot to cold discussed in part 1. No surroundings are necessary. Entropy always increases no matter what volume compartments possess and how many molecules of each gas there are. It is also the case when a solute is dissolved in a solvent to produce a solution, or when any number of substances, no matter what physical state, mix together. In other words, delta S mixing is always greater than 0 or positive. The above is an elegant explanation resulting from Bottzmann analysis. The three simple interpretations of entropy can also explain the increase in entropy during mixing in, of course, a simpler qualitative way. Mixing always increases the degree of disorderliness. For example, consider a soluble solid solute dissolving in water. The particles of the solid are arranged in space in an orderly manner. When the solid dissolves in water, these particles distribute themselves through the solvent in a disorderly fashion, resulting in an increase in entropy. And the particles of the solid are restricted to just vibrational motion, whereas they are more free to translate throughout the solution. Thus, the degree of freedom of motion increases in going from the solid state to the state of aqueous solution, leading to delta S mixing greater than 0. The energy of the particles is concentrated in a smaller amount of space in the solid, while it is dispersed in a larger amount of space throughout the solution. Thus, energy dispersal also increases, with a consequence that delta S mixing is positive. As was mentioned in part 1b, it is known at the macroscopic level that whenever a given number of substances combine together in a chemical reaction to form a smaller number of substances at constant temperature, the entropy always decreases. That is, at the microscopic level, whenever atoms combine together to form molecules or formula units, or smaller molecules combine together to form bigger molecules, entropy always decreases. In other words, every combination reaction is accompanied by a decrease in entropy. It is very easy to understand this in terms of Bottzmann analysis and his entropy equation. Let us say that the two particles in the 6 cells considered at the beginning of the finer, more precise analysis are atoms, and that they combine together to form a molecule at constant temperature. For example, 2Hg gives H2G. Since the two atoms are bonded together in the molecule, they can occupy only the adjacent pair of cells, not cells that are farther away. This reduces the original 15 possible microstates to just 5 possible microstates. That is, Wi equal to 15 decreases to Wf equal to 5. Therefore, the entropy decreases to K ln 5 equal to 1.609 K from the original 2.708 K. It does not matter what shape and size the container has. the entropy always decreases due to the essential condition that the two atoms have to be together in adjacent cells. The above decrease in entropy can also be understood qualitatively in a simpler way by employing any of the three simple interpretations of entropy. Notice that the molecule formed is more structured than the two separate atoms. Therefore, the degree of disorderliness and hence entropy decrease. When the two atoms bond together to form the molecule, one atom always has to follow the motion of the other. They both cannot move freely in their own ways as they could before their binding together. Thus, their freedom gets restricted and hence delta S is less than 0. In the case of the molecule, the energy is concentrated in space in the two bound atoms, whereas when the two free atoms move separately from each other, the energy is more dispersed. This decrease in energy dispersal leads to delta S being negative. It is easier to remember these simple interpretations of entropy rather than the more detailed Bottzmann analysis. Whichever of these three you are able to relate to, you can keep that in mind to recall that combination of atoms to form more structured molecules or formula units and of simple molecules to form larger, more structured molecules always result in a decrease in entropy. Thus, these three simple interpretations are considerably successful in helping us make sense of positional entropy. In the case of thermal entropy, as seen in part 1, they are successful in a few cases. Therefore, we should give them due respect instead of blindly attacking them, especially the idea of disorder of particles as many do. However, it is also important to realize that they fail completely to shed light in several other cases, as was shown in detail in this video series. Therefore, they constitute only an incomplete understanding of entropy. For a complete understanding, Bottzmann analysis and his entropy equation are indeed essential. Incidentally, one might wonder if the decrease in entropy during the spontaneous combination of atoms to produce molecules or formula units is a violation of the second law of thermo. No, as long as it is a closed system and not an isolated system, as was discussed in detail in part 1. In an isolated system, it cannot occur spontaneously. The surroundings are a requirement to be satisfied so that the entropy of the surroundings would increase in such a way that the net change in entropy is an increase for the system and the surroundings taken together. In part 3 of this video series, we discuss in detail a possible example of the Clausius analysis between 1850 and 1865 that led to both the verbal and mathematical statements of the second law of thermodynamics.